Welcome to this video, where we are going to review the single minute exchange of die, a technique used to reduce the setup time as well as the changeover time. The single minute exchange of die, or SMET for short, is a lean manufacturing technique used to reduce setup or changeover times in production processes. The goal is to minimize the time it takes to switch from producing one product to another, ideally to under 10 minutes, hence single minute. Let's review the evolution of pit stops in the Formula One race. A long time ago, the car was not positioned in a good spot, parts were not designed for fast changeovers, tools were not readily available, there were no standardized processes, and the team was not trained. The time was not tracked as time lost in pit stops, therefore making no difference. Now, the car is quickly positioned in the ideal spot, tools are readily available, the driver has coordinated the team for change, the pit crew team is well trained and practices often, the time is tracked religiously, and crews are graded for their speed and accuracy. Why this change? Because time is an important resource related to many other resources, including human resources, therefore, saving time means saving resources. The SAMED approach includes 6 main steps. Measure total changeover time, split activities into internal and external steps. Move external steps outside the actual changeover process, shorten internal steps, improve external steps to eliminate waste, and standardize the new changeover procedure and track it rigorously. In order to measure the total changeover time, a format should be developed. This is an example that includes the activities or actions, the duration, the activity type, that is, internal, external, or waste, and the improvement option column, which might be to eliminate, to make external, to make faster, or to make parallel, measures taken, the projected new time, and finally the projected savings in percentage. Let's see an example. An engineer is trying to reduce the setup time for an oil filter change in an industrial press, which is located at the top of the press. The engineer sees how the actual change is realized, noting that the first action is getting the crane remote control, which lasts an average of 3 minutes and 15 seconds. The second action is moving the crane towards the filter, lasting 5 minutes and 25 seconds. The operator uses it to get the tools from the first floor, and so on. The actual procedure continues with a total of 26 actions. In the end, the operator utilizes up to 1 hour, 49 minutes, and 40 seconds. The second step of SMED aims to split activities into internal and external steps. Internal steps are tasks that can only be done when the machine is stopped, that is, when the production is shut down. For example, removal of dies, change of blades or tooling, and loosening/tightening of critical bolts. External steps are process steps that could be performed during production. Thus, they could be done before or after the changeover. In fact, a high percentage of operations are usually external steps that could be done before or after the changeover. Let's think of an extruder machine. Some examples of internal steps for a changeover include screw pull-o extruder cleaning, which must be done only when the machine is off. External steps include all documentation steps, the preparation of tools, cleaning the outside of the machine, or positioning the tools near the extruder. Therefore, these steps could be done before or after the changeover. Once the internal and external steps are identified, the external steps must be moved outside the actual changeover process. For example, stage tools in the area before the changeover, so time will not be spent retrieving them during the changeover, stage dies at the machines prior to beginning the changeover, and wait until the changeover is complete to fill out paperwork. The fourth step implies that, once we define the internal steps, these should be shortened. For example, in electronic assembly, a generic wafer test process flow includes sorting, testing, fusing, inking, and a final optical inspection. The testing step used a machine with different components. A critical one is the load board, which is product-specific, meaning that a changeover is needed between different products. It requires several minutes due to the complex steps to loose and tighten the load board. Instead of manually changing this load board, that is, screwing and unscrewing the load boards, engineers implemented a CD changer mechanism, which simply changes for a specific board in a few seconds. The fifth step of SMED is to improve external steps in order to eliminate waste. For example, instead of storing tools in a central storage area, tools are stored in local areas near equipment. Instead of searching for materials that are required to perform a changeover, ensure that proper materials are provided in all areas of the plant. After improving external activities, the progress should be noted in the format. Then, the total time for the changeover must reflect an improvement. In this example, an additional 18 minutes were externalized, further reducing the equipment downtime. The sixth step implies standardizing and monitoring the new procedure. Here, new targets must be addressed with the goal of achieving them in a stabilization period. Once the new targets are achieved, it is time to set new targets in a continuous improvement cycle. SMED is highly related to lean because setups are often necessary to add flexibility to the production. Reducing setup or changeover times improves the capacity. This, in turn, can allow increased batch sizes without an additional inventory investment. Moreover, SMED reduces the overall flow time of the process and allows increased flexibility. Is SMED only focused on manufacturing processes? The short answer is no. In fact, it is widely implemented in several sectors, including healthcare. An example of SMED in a hospital is the changeover process in the operating room and patient room turnover. The equipment here is the operating room and patient room. Time equipment is running when the operating room or patient room is in use. When the operating room and patient room are not in use, the time equipment is stopped. In order to maximize the use of the operating room and the patient room, some activities are identified, including cleaning, disinfecting, and preparing the operating room and patient room. An SMED project aiming to improve the operating room changeover started to measure the changeover time, being 75 minutes, from the last stitch from a previous patient to incision in a new patient. After identifying all possible causes for a long changeover time, the improvement team organized them in a cause and effect diagram. The team decided to separate internal activities such as disinfecting the operating room and the patient room, as well as cleaning the operating room and the patient room, surface cleaning. Then, they decided to make external step of preparing the operating room, medical tools for the next surgery, and also some steps of cleaning while the operating room and patient room are in use. In addition, the team worked on standardizing disinfection procedures that were followed. After 1 year of follow-up, both the skin-to-skin changeover times for general surgery and gynecological surgery were reduced from 75 minutes of turnover to 45 minutes of turnover. That is, the time to use the operating room between one patient and another was reduced by 30 minutes, leading to an increase in the productivity of the operating room, doctors, nurses, and the hospital as a whole. For more information, please email Diego Lapa at uabc.edu.mx.